Hi everyone. Just to address your feedback from today, when we started to go over Coulomb's law and your orbital diagram, I was so confused. I didn't know what questions to even ask. Everything about Z effective did not help. So I will honestly say I think that might be on me for not teaching it or explaining it as clearly as I could have. I think I focused too much on some of the physical, like physics details. I wanted to get across some of those because I feel like I haven't discussed Coulomb's law, like the actual functional form of it, enough. But I think that that caused me to sort of obfuscate the real, the meat of the concept of effective nuclear charge. So let me kind of just quickly run through that with another example. So if I were going to draw a sketch, a very basic sketch of not even just not the sodium plus, but just the sodium atom. So sodium's has 11 protons in its nucleus. So for neutral sodium, that means it should have 11 electrons. Sodium's electron configuration is 1s2, 2s2, 2p6, 3s1. So if I was going to draw a rough sketch of how the electrons are organized into this atom, I would have my first shell. So this is my n equals 1 shell, and there should be 2 electrons in there. Then there's my second shell. So that second shell has 8 electrons in it. And then my last outermost valence shell, so that's my n equals 3 shell, has just 1 electron in it. So we kind of want to understand, or just get a very basic understanding of what types of interactions, how are things being compelled to move inside of the atom. And the way that's determined is classically would be by looking at the forces that everything experiences. According to Newton's second law, force is equal to is related to the acceleration that an object experiences. So that should determine, you know, whether things tend to accelerate in one direction or in the other. So there's two types of interactions that can occur here if I was looking at the interactions of this outermost electron, the valence electron. What type of interactions does it have, or does it experience? Well, it experiences a pull, one type of interaction between itself and the nucleus, and then there's a bunch of repulsive interactions. There's a bunch of repulsive interactions of all of the other electrons that are all in some way pushing on this outermost electron and effectively blocking some of this attractive interaction. So if I really wanted to treat this numerically, if I wanted to treat this precisely, I would need to add up all of these forces. There's a repulsive force there, repulsive force there, repulsive force there, there's an attractive force there. If I wanted to look at the net force on that this electron experiences, I would have to take all of those into account, and I have to add them all up, and it would be a big, messy equation. So one of the tricks or approximations that physicists and chemists use to sort of simplify this picture is to say, okay, these electrons, they all exist in an electron cloud of our orbitals, and essentially what we'll do is we will smear out some of these interactions. I'm going to say, okay, I'm not going to look at each of these individual repulsive interactions. I'm going to sort of average over them. Just say they all, on average, have a repulsive interaction, so that I can have one repulsive interaction, and I can have one attractive interaction to the nucleus. And if I sort of blend all of these together, what I end up with is a much simpler picture where I have a reduced effective attractive force, because there is still a net attractive force. I have 10 electrons and 11 protons. So on average, there's still a positive net charge for this last electron to experience. I'll smear all those interactions out, and I'll end with a single set of interactions between the outermost 3s electron, and I'll basically say all of those other core electrons, they all kind of get lumped down, and they can be simplified to just one single charge, one single pairwise interaction. So normally there would be a bunch of pairwise interactions with effective nuclear charge. The idea of effective nuclear charge is to average over all of these interactions and boil it down to a single effective interaction with an effective nuclear charge instead of the actual nuclear charge. Conceptually, that's all effective nuclear charge is trying to do, is give us a rough picture, a rough idea of how much of a pull, how much of an attraction one electron has to the nucleus, while also trying to take into account some of the repulsive interactions that the core electrons exert on that outermost electron. So that's kind of the basic idea of effective nuclear charge. We're going to continue to use that as one of our tools for explaining periodic trends. So on Wednesday, I'm going to talk about some of the other periodic trends for ionization energy and electron affinity. Those trends we can also explain in terms of just the number, the size of the orbitals, like going into larger and larger shells, and also the magnitude of the attractive interaction, how strongly one of the electrons is being pulled towards the nucleus. Those will we can explain periodic trends for other properties using this idea of an effective nuclear charge that decreases as you move through the periodic table. Why do we need to know Coulomb's law if we won't do calculations with it? Coulomb's law and force-charge proportionality is confusing. What situation would we use this in? What are we calculating? Okay, so I do want to clarify this. You're right. We're not going to do any calculations with Coulomb's law. But I would say it's wrong to think that the only, so this is me being sort of, maybe, I hope not patronizing or pedantic, I don't know which the correct term is I'm looking for here, but I hope I'm not diminishing how people approach equations, but I would say that you're selling the equation short if your only interpretation of its value is if you can calculate things with it. So yeah, we won't be calculating things with Coulomb's law, but then again, what is a law? A law is a general observation of natural behavior. So the general relationship that Coulomb's law tells you is that if you have two charges, so I'll call this charge 1 and charge 2, the magnitude of their interaction, how strongly they attract or repel each other, is determined by the sizes of these charges. That in of itself is a big idea, that the magnitude of the force is proportional to the size of these charges. Just like if you learn about gravity, the magnitude of the gravitational force is proportional to the mass of an object. If it has more mass, it experiences a greater gravitational force. So same basic idea with Coulomb's law. That by itself is something that we are applying here to sort of explain, okay, the magnitude of this force, that the attractive force that my last electron experiences, it's dependent upon the size of the nuclear charge. Let me say that again. The magnitude of the force that this electron experiences is dependent on the magnitude of the nuclear charge. The stronger the force, the more it's being pulled towards the nucleus. The trend for effective nuclear charge is that as you go across a period, go across a row, the effective nuclear charge, the magnitude of that charge increases. So the magnitude of the attractive force increases, so on average the electrons are pulled closer and closer to the nucleus. So that's a general rule, a line of logic, a rule of like rationalizing to yourself as one thing increases, how does something else increase or decrease? And that's something that you don't need to do any calculations from, but it's that way of proportionality and thinking about how does one property depend upon another property. That's what's encapsulated in an equation, and that's true irrespective if you're going to do any calculations with it. So that is why I wanted to discuss Coulomb's law in a little bit more detail. We're using it now to discuss effective nuclear charge. We'll use it a little bit later to discuss things like dipoles, like the fact that water has, well, I think I've mentioned this in passing, that water has basically to some extent behaves like a bar magnet. It has a positive end and a negative end, and that's something that we'll explain later in terms of electronegativities. We're going to use the concept of charges repelling or attracting each other to explain things like molecular geometry, how atoms like to actually physically arrange themselves in three-dimensional shapes when they make a molecule. You guys will use it later in organic chemistry when you start looking at more subtle molecular interactions, like how do bonds like to orient themselves, how do they like to rotate and twist around, what's their lowest energy state, how do they minimize their forces. All of that is in some way can be derived or rationalized by looking at Coulomb's law. So basically, the force is inversely proportional to the distance. So as objects get further away from each other, the magnitude of the force tends to decrease. So if I have two sets of charges, if I have two charges and I want to find the lowest energy state or find the lowest amount of repulsive interactions, they will tend to spread out to get as far away from each other as possible. The distance between them tends to increase. As this increases, the force, the repulsive force, would decrease. So again, that is a way of thinking that you can rationalize to yourself just by looking at the functional form of Coulomb's law without having to do calculations. And that is something that I would like people to start being able to do, or I think it's a valuable skill that you guys can potentially apply. So that's why I'm teaching it sort of in terms of proportionalities rather than as an actual equation that you'll do calculations with. Because again, that way of thinking, the Coulomb law, I think this is one of the big ideas in chemistry. I admit I haven't thrown that slide up in a while, but one of the big ideas of chemistry is that the Coulomb force is the fundamental force of interaction in chemistry. It's all about this Coulomb force, this electrostatic force. And so yeah, we'll be using that to rationalize a lot of physical behavior. Does effective nuclear charge have anything to do with the size increasing as you go down the groups? So yeah, I didn't mention this when we were talking about the trend to go down a group. You can relatively easily explain that trend by just saying, look, as you go down a group, as you go down to the column, the electrons of that atom are now in larger and larger shells, or rather larger and larger orbitals. So that you can explain without referencing effective nuclear charge. But it is true that effective nuclear charge also decreases on average as you go down a column. So the general trend for Z effective is to increase. I can't write this. The trend for effective nuclear charge is to increase going up the column, and it increases going across the row. So it has the exact same opposite, or the exact opposite trend as atomic radius. Atomic radius increases going down a column, and it increases going back across the row. And again, the way we understand that is that, okay, the radius is determined by how tightly the electrons are being pulled towards the nucleus. That is determined by the magnitude of the Coulomb force, which we can understand we can predict as following a certain trend by understanding what's going on with effective nuclear charge. So effective nuclear charge tends to decrease down a column because the effective nuclear charge decreases, the electrons aren't held as tightly, so they can get further from the nucleus, so the atom gets larger and larger. So that also does come into play for going down a column. Does Z effective equal the force of shielding? Does effective nuclear charge equal the force of shielding? Not quite. I actually liked Leo's definition, or Leo's interpretation of effective nuclear charge as the net charge that occurs after you take into account the force of shielding. So the shielding force is all of these repulsive interactions. That's the shielding force, if you want to think. There is, I've never heard the term shielding force, or the force of shielding, but I think it's a valid term to use. If you're going to say, okay, what is the force of shielding? It's all of these repulsive interactions. That's the shielding effect, because otherwise this electron would feel a full plus 11 charge. After you take into account shielding, you have only a plus 1 effective nuclear charge. So this is the effective nuclear charge. This is the shielding force. So I wouldn't equate Z effective and shielding force. I would say, if there was going to be any type of relationship, I would say, well, we've said this before, that it's equal to Z minus the effect of shielding. So it's not equal to, it's sort of a result of, I would say, a shielding, but it's not equal to the force of shielding. Is Z effective, if Z effective is greater, wouldn't that mean that electrons are closer to the nucleus? So yeah, if Z effective increases, does that mean electrons get closer to the nucleus? Yes, short answer. As the effective nuclear charge increases, the magnitude of this force increases. So as the force increases, the radius tends to diminish. They tend to get pulled closer to the nucleus. So again, we'll say that one of my charges can be my effective nuclear charge. So as effective nuclear charge increases, the force tends to increase, which means that the radius tends to decrease on average. So yeah, they would get pulled closer to the nucleus. As you go across, I think you answered your own question here because you circled it, but I'll reiterate it. As you go across a period, does effective nuclear charge decrease or increase? It tends to increase. As you go across the period, the number of protons increases, but the number of shielding electrons remains the same, because the shielding electrons are all of your core electrons. That core is set within a single period, within a single row. As you go across the row, you're adding electrons to the valence shell, the outermost shell. So you're not increasing the shielding effect. What defines core electrons? Okay, core electrons are anything that's not a valence electron. So let me define valence electrons. Valence electrons are the outermost electrons. So there's a couple of ways, a couple of definitions, or a couple of ways to think about valence electrons. They are the outermost electrons. They are the electrons in the highest N shell. So they are electrons that are in the outermost shell. So for the example of sodium, this 3s electron, that one electron that's in a 3s orbital, that's the valence shell, and those are valence electrons. What is a core electron? A core electron is anything that's not a valence electron. So all of these would be considered core electrons. Just like, the Earth's core is the center, or you guys know what core is. So those would be, those are what core electrons are. Again, we will usually like to focus on the valence electrons. Those are what's going to determine most of the chemistry in terms of gaining and losing electrons. Those are the ones that are on the outermost shell, so those are the ones that are the easiest to strip away, remove, and they're the places where I have empty orbitals where I can put electrons on. The core orbitals are all filled up. So it's mostly the valence electrons that we'll care about in terms of chemical behavior. Everything else is considered a core electron. I'm confused by the language. What is the difference between S1 and S2? So I think you're referring to the notation for electron configurations. The superscript tells you the number of electrons in that particular orbital or subshell. So for instance, I mentioned that the Pauli exclusion principle, so we discussed this on Friday, that the Pauli exclusion principle essentially asserts that you can put 2 electrons in any particular orbital. So there's a 1s orbital, I can put 2 electrons in there. There's a 2s orbital, I can put 2 electrons in there. There are 3 2p orbitals, and each one of those I can put 2 electrons in. So I can put 6 electrons total into the 2p subshell. Let me, I just want to check if I want to erase that or not. I'm not going to, okay, I don't need this anymore. So if I was going to draw my orbital diagram here, I would have a 1s electron, and I can fit 2 electrons into there, 1 spin up and 1 spin down. Then I have my 2s subshell, I can fit 2 electrons in there, 1 spin up and 1 spin down. Then I have 3 2p orbitals, each one of them can be filled with 2 electrons. And then finally I have this 3s orbital, and I can put 1 electron in there. So again, this is specifically the orbital diagram, or this is a combination of orbital diagrams and energy level diagram. For sodium, because I have 2, 4, 6, 8, 10, 11 electrons, so yeah, that's sodium. So what is the notation? Again, the notation basically tells you if you have 1 electron in that orbital or 2 electrons in that orbital. For something like 2p6, when you're writing electron configurations, you normally don't say, you could, to be fair, you could write it like this: 2px2, 2py2, 2pz2. So I could represent 2p6, that whole subshell. I could represent it like this. The idea is that each one of these refers to a slightly different p orbital, because remember that there's 3 p orbitals and they're perpendicular to each other. One points up, one points this way, and one point's perpendicular to them along the x, y, and z axes. So there's that. I'm still unclear about the equations. So I'm not certain if you're referring to the Coulomb equation or to this approximate form of how to calculate or how to approximate effective nuclear charge. I hope during the course of this feedback discussion, I've clarified a little bit about the Coulomb equation. For this equation, I think Leo put it nicely. The effective nuclear charge is sort of like the net charge that an electron experiences. It should feel an attractive charge from the nucleus. Again, Z is your atomic number. But then you say, okay, there are a bunch of other electrons between that electron and the core. There's a bunch of other electrons. I admit, I just erased it, but there should be a bunch of other electrons here, and those electrons essentially negate or cancel out some of the nucleus's full charge. So you subtract off the number of shielding electrons, the number of core electrons, and that's how you can approximate the effective nuclear charge. And again, it really is, this equation is not really an equation. I mean, it is an equation, but it's an approximate equation. The effective nuclear charge is approximately equal to the nuclear charge minus the number of core electrons. So again, you can think about this as like your net charge after you subtract off some of the shielding electrons. And the last point here was about electronegativity. I admit I did not do that topic justice. And that's okay. We'll definitely double back and talk about electronegativity more once we've started talking about chemical bonding. Elements do have a particular property called electronegativity. As I mentioned, it's a general measure of how much an element likes to pull electrons towards itself. It is kind of arbitrary. You'll see when we discuss it, it's kind of Linus Pauling, a famous chemist slash physicist, kind of came up with it as a general scale, and he kind of just said, well, fluorine is the one that's in the top left-hand corner, seems to on average like to gain electrons the most. I'll set that as having the highest possible electronegativity, and I'll, for no particular reason, give it the value 4. So it's very vague, but we'll talk more about that again. We'll talk more about that later when we get into chemical bonding. Electronegativity specifically refers to how much an element tends to pull electrons towards itself if it's in a bond. Before we talk about electronegativity, we're going to talk about other periodic trends, and those are ionization energy and electron affinity. And those both also deal with how much elements like to gain or lose electrons. Those are a little bit more quantitative. They're in terms of energies, so we'll talk about those a little bit more quantitatively on Wednesday, is my plan. So until then, I will see you all on Wednesday, unless you're in my lab section, in which case I'll see you either later today or tomorrow. Thank you very much for your feedback, and I will see you all soon.